Hello and welcome to this video on solitonic dispersive waves in nonlinear optical fibers. In the previous video, we investigated supercontinuum generation, which occurs when you launch a short high-power pulse into a nonlinear medium and its spectrum is broadened due to various nonlinear effects. In that previous video, we saw that, at least for a particular pulse and a particular medium, the evolution is initially dominated by self-phase modulation, whereupon the Raman effect becomes noticeable and creates a so-called Raman soliton, which continuously shifts its own frequency towards lower and lower values. We also saw that some additional light was generated over here at a higher frequency, and I initially attributed this phenomenon to four-way mixing, but it turns out that's actually not the mechanism causing this additional light at 320 in this case. And basically, we're going to explain in this video how we get this additional light. Now, to highlight what's going on here, I've created a simpler simulation where we're launching a fundamental soliton into a medium where there's no Raman effect, no self-steepening, and where the value of beta 2 is negative, and that there's no higher order dispersion terms at all. In that case, the signal of course just evolves as an ordinary soliton where no change occurs in the spectrum. But if we change beta 3 so it's not zero anymore but positive, we get this additional light appearing over here at a higher frequency as we saw in the previous video. And if we flip the sign of beta 3, we can see that this same light seems to occur over here at a lower frequency. And if we change the shape of the pulse to be a Gaussian instead of a hyperbolic secant, and we also make beta 3 positive, we still get this light present over here at the higher frequency as before. So clearly there's something going on here where launching a pulse into the medium generates additional light based on the value and sign of beta 3. So could this just be forward mixing? Well, it turns out the answer is no, because if we launch a fundamental soliton into one of these media with a negative value of beta 2 and a positive value of beta 3, we see a huge amount of gain happening here at a very narrow range of frequencies. In fact, this particular one here seems to experience around 60 decibels of gain compared to where it starts down here. And if forward mixing was the mechanism governing this, we'd expect the exact same thing to happen when we launch in a continuous wave signal. But if we try that, clearly that's not what actually happens. In this case, I've launched in a continuous wave signal that has the same peak power as the soliton from before, but obviously spread out over the entire time duration of this simulation. But we still don't see any significant power transfer from the main frequency here into the secondary one down here. And note that the relative intensity of these two frequencies is the same as it was in the soliton simulation, but there's really no significant power transfer. The only thing we see is a little bit of modulation instability happening right here. So once again, because we don't see any significant power transfer when we have continuous wave signals, it's not four-way mixing causing this initial effect that we saw earlier. So if it's not four-way mixing, what's actually going on? To understand this, let's take a look at the time domain behavior of this pulse evolution. So we're launching a signal into the fiber here, and for the most part, it seems to just be a pulse that propagates forward and maybe delays itself just a little bit. But we also see these really significant streaks of light appearing and delaying themselves to later times here. And this actually looks like just a continuous wave signal. And that's a bit easier to see if we look at the spectrogram evolution of the same signal. We can see that we start out with a soliton right here, and then it immediately begins to generate continuous wave light at a higher frequency that then starts to trail behind, probably because of the positive value of beta 3. And also it seems to delay itself slightly here and maybe even shift its signal a little bit. I think this might be a sort of energy conservation phenomenon where, because we generate more energy here at a higher frequency, the entire soliton has to shift a little bit towards lower frequencies. But the main insight here is that we have a soliton that generates continuous wave light. In fact, that is fundamentally what's going on here. We have a soliton and a continuous wave signal that are propagating with the same spatial frequency, which allows for coherent transfer of power from the soliton into the continuous wave, thanks to the nonlinearity. Now, this is the phenomenon referred to in the literature as a dispersive wave. So it's very natural to ask, well, for which temporal frequency is this phase matching actually achieved? Because we saw that it only happens for a very particular range of continuous wave frequencies. So I'm going to explain that in just a moment, but I want to also highlight the paper I got this information from. It's linked in the description to one of the original papers describing this phenomenon. Before we get to that, I want to just complain a bit about terminology, because this phenomenon in the literature is referred to as dispersive waves. But I actually think that calling them solitonic dispersive waves would have been a bit more informative, because this emphasizes that you need a soliton, or at least as efficiently, soliton-like signal for this process to actually arise. It's simply not enough to have any kind of signal. It needs to be fairly pulse-shaped, as we saw earlier with the continuous wave example. So anyway, that little complaint aside, just remember that when you see dispersive waves in the literature, really what they're saying is that you need a soliton to generate these dispersive waves. So, with regards to the question of phase matching, let's take a look at the general expression for the spatial frequency of some signal that's propagating through a nonlinear medium. In general, we can write this as a sum of the linear contribution that's determined by the design of the waveguide and a nonlinear contribution that's determined by the intensity and the duration of the signal that you're launching in. Now, we've seen earlier that in a typical medium, you can determine the value of beta for any particular frequency you might launch in, and then Taylor expand it around a carrier frequency, for example, here labeled by omega naught. And we get all these different terms where beta naught determines the phase velocity, beta 1 determines the group velocity, and beta 2 is the group velocity dispersion that governs how much the pulse spreads out as it propagates forward. And of course, you also have higher order dispersion terms here. But the nonlinear contribution to this total spatial frequency is usually quite complicated, because in the time domain, we've seen in the nonlinear Schrödinger equation that the nonlinearity scales with this product of the power envelope of the pulse width itself. And if we translate this to the frequency domain, that becomes a double convolution of the spectrum of the pulse width itself. So typically for any general pulse, this is going to be quite a complicated calculation. But it turns out there's a special case that's very easy to handle, namely the case of a fundamental soliton. Because in this case, when you have n equal to 1 and the dispersion length and the nonlinear length are identical, we know that the signal described by a hyperbolic secant envelope with this extra phase factor and a very particularly chosen amplitude will propagate through the medium in a way that actually ignores the value of beta 2. Or what we can also say is that the nonlinear contribution to the spatial frequency will be this constant contribution from the exponential plus some additional contribution that exactly cancels out the contribution of beta 2 from the linear part of the calculation. So in total, for a soliton, we can write the total spatial frequency at this extra contribution here, plus the first, or as you said, the zero and first order terms, and then we can simply cancel out the second order term, like so in the whole expansion. And just for convenience, we're going to rewrite this term here as beta naught NL to emphasize that it's a contribution to the beta naught parameter from the original calculation. But anyway, the point here is that particularly for a soliton, the contribution beta 2 is cancelled out by the nonlinearity. In fact, this is kind of the definition of being a soliton. It's some kind of signal that allows you to cancel out the broadening due to beta 2. Now, it turns out we can actually also, at least approximately, ignore the contributions from higher order dispersion terms. And the logic here is that if you have any actual signal being launched through a fiber, then, at least if it's reasonably pulse-shaped, you can always approximate it as a soliton plus some additional field that's basically the difference between the actual field and this hypothetical soliton. So essentially, when you look at the effect of beta 3 and beta 4 and so on the actual field, you can always approximate this as just a completely unaffected soliton plus this additional field that then absorbs all of the impacts of beta 3, beta 4, and so on and so forth. So anyway, the point is just that you can always approximate any sort of reasonably pulse-shaped signal with an underlying soliton, and then look at the phase matching between that soliton and some other field that's present inside of the medium. So essentially what we're doing here is we're looking at the phase matching between the soliton and a continuous wave signal over here. So here we have the spatial frequency of the soliton, and here we have the spatial frequency of the continuous wave light. And so we can start out by simply cancelling out the beta 0 and beta 1 terms like so, giving us this equation where if we can solve this, we can find the temporal frequency where the dispersive wave should arise. If we assume that the nonlinear contribution is fairly small and that all dispersion terms greater than beta 3 are simply 0, we get this much simpler equation, which we can easily solve for the dispersive wave frequency like so. We can see that it depends on 3 times the ratio of beta 2 to beta 3. And it turns out there's an interesting connection here with the zero dispersion frequency, because if you calculate that using the following formula, it's very easy to show that the zero dispersion frequency also depends on this ratio of beta 2 to beta 3, but without this factor of 3 out in front. So the point is that if, for example, we launch a carrier or a soliton with a carrier frequency of 200 terahertz into a medium where the zero dispersion frequency is at 201 terahertz, then the dispersive waves should arise over here at 203 terahertz. And here I've simulated exactly that. So we have a soliton with a certain carrier frequency, and here I've numerically calculated the theoretical zero dispersion frequency just by evaluating this expression here, and then also calculated the theoretical dispersive wave frequency by using this expression. And we can see that indeed the dispersive wave frequency, we see this little orange spike, is 3 times further away from the carrier than the zero dispersion frequency, when at least we can neglect the nonlinear contribution and all higher order dispersion terms. So just for good measure, I've also created a quick graph here in Desmos that illustrates this in a bit more detail. So in this graph, the green curve we see here is the linear contribution to the spatial frequency, and the purple curve is the dispersion experienced by a soliton. And you can see that if we increase the nonlinear contribution, the purple curve shifts upwards a little bit. The black curve here is simply the difference between the green curve and the purple curve, and we can see that it crosses zero right here. So this is where we expect the dispersive wave to arise. And also we can see that if we make the nonlinear contribution very small, then the theoretical dispersive wave frequency marked here in red is a very good approximation to the zero crossing here. But if we make the intensity of the field much stronger, we can see that it shifts further to the right away from this theoretical line here. And also we can see that it's 3 times further away than the zero dispersion frequency like so. So we have linked this in the description as well, so you can go and play around with that at your own time. So what more can we say? Well, something that puzzled me a little bit before making this video is why we don't see any cross-phase modulation term on the right-hand side of this expression. Because if we think about it, we start out with this nonlinear contribution on the left-hand side, which essentially is the self-phase modulation contribution for the soliton onto itself. And so if we subtract that to the right-hand side, we get a factor of -1/2 here in this equation. But in general, I feel like if we have a very strong signal, which a soliton would be, then we should also have a cross-phase modulation term on the right-hand side that explains how much the nonlinearity causes a delay in the phase of the continuous wave signal. And usually I think this should be like a factor of 2 compared to this one over here. So in general we should get something like maybe a factor of 3/2 over here on the right-hand side. But it turns out that if we write down the expression for the phase matching condition, try and solve it for the red line right here, if we set S to be 0, which is equivalent to simply ignoring the nonlinear contribution altogether, we can see that it kind of approximates the actual frequency at which the dispersive wave arises, but it doesn't do so that well. But if we include the -1/2 factor, which is what we saw in our earlier calculation, then it gets a little bit better. And in fact, if we make it even more negative to -1, it becomes even better than that. But if we set it to a value of 1.5, which is what you would expect if cross-phase modulation for CW light is also included, the approximation actually becomes a lot worse. So I don't really understand why it is that we don't get a continuous wave cross-phase modulation term on the right-hand side, but clearly neglecting it is actually superior. So as I said, I don't have an explanation for this, but it could be a potentially interesting research question that some of you guys might want to analyze, maybe even write a paper or possibly a thesis about. If you do, I'd be very interested to see what you figure out. Now, my own sort of hunch for why this is happening would be that we're actually not dealing with a sort of coherent power transfer from a soliton into a continuous wave, but actually from a soliton into this additional difference field here. That's what's actually sort of absorbing the power from the soliton, and therefore the calculation is a little bit different than you might expect. And again, this is just a complete hunch, but it could be a starting point for some of my viewers to check out if you're so interested. So anyway, another interesting thing about dispersive waves is that you can't just get them at a single frequency, you actually get them at multiple frequencies at the same time. So in this case, I've neglected the value of beta 3 and simply included the value of beta 4 in this expression here. So if we use the same trick as before, we can neglect the nonlinear contribution and then try to solve this formula here for the frequency at which dispersive waves arise. And if we do that, we find a quadratic here, at least if beta 4 is positive. And ultimately we find 2 different values for the possible dispersive wave frequencies, which also depend on the distance to the zero dispersion frequency, but now with a factor of 2.5 instead of a factor of 3. And if we run the simulation as before, we can see that we get 2 different dispersive waves, one here at a lower frequency and one at a higher frequency. And as predicted, they're 2.5 times further away from the carrier than the zero dispersion frequency is. Another kind of interesting thing I discovered while just playing around with the simulation is that it seems you can do reverse dispersive waves. So if you launch in a signal here at a value where the beta 2 value is positive, and where beta 3 is still positive, we can see that power seems to get transferred from the carrier and into a wave over here. But now the resonant frequency and the carrier are sort of equidistant away from the zero dispersion frequency, which doesn't really match the distance that we saw in the previous analysis. So again, I'm not really sure why this is occurring, but there are some papers I found that go into this in a bit more detail, or at least determine that, yeah, this is something that actually happens in real experiments. So once we understand all of these factors here, it's possible to generate something called, or what you might call, a phase matching map. So the idea is that for a given waveguide design, we can compute the linear contribution to the spatial frequency for all possible carriers that you can launch in. And then knowing that, we can compute the values of beta n for all possible carrier frequencies you can launch into the medium. And then if we know the peak power of the signal, you can compute the nonlinear contribution and simply solve this equation for all possible frequencies where dispersive waves might arise. That's what's done in this particular paper here, where they're launching a pulse into a hollow core fiber with different gas pressures of argon inside. Then they determine all of the frequencies at which they expect dispersive waves to arise. And you can see that from this graph here, if they launch power with a carrier frequency corresponding to 1080 nanometers into this medium with a pressure of 8 bars inside, then the dispersive waves arrives over here at in the UV range as well as in the near infrared range. And so you can simply repeat this process for all possible values of the input frequency and then draw this map of all the resonant frequencies that arise. So for example, in this case, we can see that if the pressure is 5 bars, then if they launch light with a carrier frequency of 980 nanometers into this hollow core fiber, then they can expect dispersive waves to arrive around 300 nanometers and 750 nanometers up here. And we can also see that for this particular case, the UV resonant frequencies are much more sensitive to the pressure than the near infrared frequency is up here. And I think this also highlights another advantage of exploiting dispersive waves simply for frequency conversion, because note that they're launching light in the infrared range into this medium and they get light in the UV range coming out. So they're basically tripling the frequency of the light coming in without actually exploiting something like third harmonic generation. Now I'm pretty sure that third harmonic generation would be more efficient, but it still shows that we can actually get pretty significant frequency conversion just by exploiting a simple nonlinearity and some dispersive properties of the medium. Finally, I want to highlight just a very interesting analogy between dispersive waves and Cherenkov radiation that happens in nuclear reactors. So in nuclear reactors, it's possible for electrons produced by fission reactions inside of the core to propagate through the surrounding water with a speed that's higher than the speed of light in the water. And this causes essentially an optical shock wave that forms this kind of cone, and the frequency of this is perceived, at least to the human eye, as being blue. Now, something similar happens when you have an airplane that propagates through the light, through the air, faster than the speed of sound, sorry. And so you get this sort of cone of like a shock wave that propagates through the air. And finally, essentially the same thing is happening here for the soliton propagating through the nonlinear fiber, because the spatial frequency of this soliton would be greater than a continuous wave otherwise would be. So the reason here is simply that we get this extra term here due to the nonlinearity, and we also cancel out this negative contribution due to the dispersion. So the spatial frequency of the soliton is higher than otherwise would be, and then we get this shock wave of light that rises over here. And this is also described in that paper I mentioned earlier that you can go check out in the description. So if you found this video on solitonic dispersive waves interesting, feel free to check out some of my other videos over here and stay tuned for more. Bye bye.